Morning, students. Today we shall discuss inductor filter. In our last class, we have learned how a RC filter or a capacitor filter works. Today we shall discuss inductor filter. The filter consists of only an inductor in series with the load. For inductor, it is when you decide the value of the inductor value is targeted for the particular AC frequency that you want to route. It is targeted for that particular frequency component. Now, what is that target frequency component? In half-wave rectifier output, we have seen earlier when we discussed the half-wave rectifier, the strongest AC component is the cos omega 0t component. That means its frequency was equal to the input frequency, and for domestic power it is 50 hertz, and the amplitude of it was Vm by 2, if you remember from your earlier notes. Vm, where Vm is the peak value, 0 to peak value of the input or the output of the transformer secondary. So if this is the primary or predominant AC component, we shall consider this component. So the rectifier output, what is this component is VAC is Vm by 2 cos omega 0t, and we know half-wave rectifier DC output is Vm by pi. This is known, right? Now, next step. When you consider the DC input, this rectifier input comes here, It's a DC component when it passes through the inductor. You know that an inductor impedance is practically 0 for DC, right? So, DC output will be same as the DC input. So, output DC, VODC, is also Vm by pi. Fine? And AC component is Vm by 2 is the amplitude. So, what is the RMS value of this AC component? Is Vm by 2 root 2. Because RMS value is always 0 to peak value divided by root 2. Okay? Then, what is the output RMS? Now, this is the input RMS, V in. This is the input RMS, Vm by 2 root 2. Output RMS will be, you just use the series equation. This is the input, which is V in AC RMS. That should be divided by the total impedance of this path. Total impedance of this path is under root R square plus omega square L square. I hope I don't have to deduct these equations. This is R is this resistance, and impedance of L is omega L, and both squared under root is the total impedance of this series line. So V in AC RMS then divided by the total impedance of the series path multiplied by this series resistance R is the output AC RMS. Now, V in AC RMS is this Vm by 2 root 2. So, it is Vm by 2 root 2 multiplied by R divided by under root R square plus omega square L square. So, we got AC RMS. Then, what is the ripple factor? Ripple factor is the output AC RMS divided by output DC. That means the ratio of AC to DC. That means this whole value, Vm by 2 root 2, R by under root such and such, and DC was Vm by pi. So that divided, when you divide it, it becomes pi by Vm. So it becomes pi by 2 root 2. This pi and 2 root 2, Vm and Vm gets cancelled. And if you take R to the denominator, it becomes 1 upon whole under root 1 plus omega square L square by R square. Now, pi by 2 root 2 is 1.1, 1.11. So it is 1.11 whole under root this factor. So this is the ripple factor after the inductor filter, right? What you must note that ripple factor improving means ripple factor should be less. Ripple factor improves when omega is more, L is more, right? And R is less. That means for lower load resistance, ripple factor is better. This is a special criteria of this inductor filter, that load resistance, which in turn is the input power resistance of the device that you are using, its resistance should be low. And omega should be high, L should be high. Too high, there is a problem, because normally in the market, high value of inductor is not easily available. And omega should be omega, and the higher is the omega, better is the ripple factor. That means what it means. Coming back to the AC component, we have taken the primary predominant AC component is cos omega 0 t. It has also AC components of 2 omega 0 t, 3, 4 omega 0 t, etc. And this equation shows that if omega 0 t is filtered out, then the higher harmonics will be filtered out better. That is the consequence of this equation, right? This is the ripple factor, or you could say final ripple factor with an inductor filter and a half-wave rectifier. If the rectifier is a full wave, then what is the ripple factor? So full wave rectifier, we have seen earlier, the DC component is 2 Vm by pi. And predominant AC component is 4 by 3 Vm by pi cos 2 omega 0 t. That means its predominant AC frequency is double the supply frequency. DC is 2 Vm by pi, and AC RMS is 4 Vm by 3 pi root 2. So this is the voltage that, this is the rectifier output, and which you are giving here at V in. Then it goes into the inductor and the resistance, right? Frequency VAC here is 2 omega 0. So impedance of the inductor mandate, it is 2 omega 0 L, right? That means in mandate, in half-wave rectifier, impedance of this inductor was omega 0 L. Now it is 2 omega 0 L. So what is the output AC? If this is the input AC, 4 Vm by 3 root 2 pi, then this is VAC RMA multiplied by R divided by whole under R square plus 4 omega square L square. Mandate in case of half wave, it was only omega square L square. So once again, it is 4 Vm by 3 root 2 pi multiplied by this factor. This is the output AC. That means the AC component available here. Right? And so for DC, what is the ripple factor? AC by DC. AC component is this component, and DC was 2 Vm by pi. So it is becomes here pi by 2 Vm. So this becomes 2, and this 4 gets cancelled. You have only 2 left here. So 2 by 3 root 2, Vm and Vm gets cancelled. 1 by 1 plus 4 omega square L square by R square. This factor is equal to 0.47, right? So now compare, this is 0.47 divided by this, and for half-wave rectifier, it was 1.11 divided by this. That means ripple factor is in full-wave rectifier with the same components is double better, right? This is inductor field. Now, since we have a little time left, what we shall do, we shall see another filter. We have seen capacitor filter, we have seen inductor filter. Now we shall see L section filter. What is L section? Mind it, it is also called LC filter, but also called L section filter. With capacitor filter, we found the ripple factor improves with higher load resistance, that will higher value of R. Whereas with inductor filter, it appears that ripple factor improves with lower value of R. That gives an idea. Hence, our intuition says ripple factor become independent of load resistance if both types of filters are combined together. So, this idea, right? So, this is a capacitor filter, this is an inductor and a resistor. They are combined. We shall find out what is the ripple factor. First, we start with half-wave input. Half-wave input, DC is Vm by pi, no doubt. And if this is Vm by pi here, DC, what is the output here is also Vm by pi. Because capacitor does not conduct DC and impedance of inductor for DC is negligible. So output DC is also Vm by pi. Finally, when we deduct the ripple factor is output AC by output DC. So output DC we got. Let us now find out what is the output AC. Now input AC here, we have seen earlier in case of half wave, is Vm by 2 cos omega 0 t. And RMS value of this Vm by 2 root 2. Fine. Now, value of capacitor is so chosen that impedance of this capacitor XC is much, much smaller than R. So that these two in parallel combination, it's almost equivalent to XC only because XC is very, very small. Right? So if these two considered together is XC, ignoring the value of R, and AC input here is Vm by 2 root 2, then what is the AC output here? Is Vm by 2 root 2 multiplied by XC, this is XC, divided by XC plus XL, right? So what is the ripple factor? This AC divided by this DC. AC is this and DC is this. So it is pi by 2 root 2 XC divided by XC plus XL. Then there is next design factor. Find here, this ripple factor is independent of the load resistor. That is the beauty of L section filter or LC filter. Here, ripple factor will be same irrespective of what is your load. That means where you connect your rectifier. That is the beauty of this L section filter, right? Also, design factor is, it is so chosen inductor value and capacitor value that XL is much, much more than XC. So XL plus XC can be considered to be XL. So if this XL plus XC is replaced by XL, this becomes pi by 2 root 2 XC by XL. That means if you consider this design factor, that impedance of inductor is much, much more than impedance of the capacitor, then its ripple factor equation is very simple. Pi by 2 root 2 XC by XL, right? Next, we shall go to another filter. I hope you can keep your patience. We have seen capacitor filter, we have seen inductor filter, we have seen L section filter, we go fourth one, the pi section filter. And I promise you, this is the last one. I'll not bother you any further. This is a pi section filter. Pi section filter is actually a capacitor filter. The first one we have learned, and then followed by a L section filter. So there is no great invention. It is the same permutation, same filter permutation combination. Here, output of a half-wave rectifier or rectifier, remember that it was a sawtooth wave. And sawtooth wave of peak-to-peak value, we consider 2 VRP. You remember the sawtooth, right? And if you find the Fourier components of a sawtooth wave, this is the equation. I am not deducting the Fourier components for you because it's a little lengthy, but this is the equation. Deduct it yourself because deduction of Fourier components is not very difficult. Only you have to be patient and do integrations. So here you find the primary component is omega 0 t. It means if we have a 50 hertz power supply, then primary component of the sawtooth wave is 50 hertz. We consider the most significant part as the VRAC. That means this is the most significant part. We consider it as the input to the L section given for further filtering. So now this part is the input to the L section. So what is the AC here? Is 2 VRP by pi sine omega 0 t. That is the input to this is the L section. And this is the input to the L section. Now for L section, we have already deducted the formula. If this is the input to the L section, it's RMS 2 VRP by pi root 2. Fine. And in case of half-wave rectifier, we have seen earlier when we discussed the capacitor filter, that 2 VRP is the peak-to-peak value of the sawtooth wave, is IDC by FC1. This is a C1, where F is the frequency of the supply. Therefore, that means this one, VRAC-RMS, this 2 VRP is replaced by IDC by FC1. So it becomes IDC divided by pi root 2 FC1. So this is a VAC-RMS, right? Now, due to the following L section filter, we have just derived the L section. I'll show you. We have just derived the L section equation. This is the L section equation. This is the L section equation, pi by 2 root 2 XC by XL, right? So now it becomes, this is IDC by pi 2 root 2 FC1 multiplied by XC2. Now this is C2, XC2 by XL. So this IDC root 2 by 2 pi FC C1, XC2 by X1. So I multiply, finally I have IDC root 2 XC1, XC2 by X1, right? So these are the C1 is this capacitor, C2 is this capacitor, L is this inductor. So this is the AC-RMS of output here, right? And what is the output DC? Output DC is IDC, current DC through the resistor multiplied by this resistor. So we have IDC, we have output DC voltage, we have output AC voltage here. And their ratio is the ripple factor. If you divide this AC voltage divided by the DC voltage, you have 2 root 2 XC1, XC2 divided by RXL. This is the ripple factor of the pi section filter and for half-wave rectifier. For full-wave rectifier, only little change. The first frequency is 2 omega 0 t. So AC-RMS is 2 VRP by pi root 2, same as half-wave rectifier. And for rectified full wave, we have learnt in capacitor filter lesson, 2 VRP is equal to IDC by 2FC1. Therefore, this ACRMS, this 2 VRP is replaced by this factor, IDC by pi 2 root 2 FC1. Now, due to the following, after this is the ACRMS here, and then there is a L section filter. So, what is the output AC? Output AC is this input AC multiplied by XC2 divided by XL, right? So, finally, it becomes this factor IDC by root 2 XC1, XC2, etc. Okay? And once again, like we have done earlier, output DC voltage is IDC into resistance. So what is the ripple factor? This AC voltage divided by this DC voltage, it is 1 by 2 root 2 XC1, XC2 by RL. What was the value for half-wave rectifier? For half-wave rectifier, value was root 2 multiplied by this factor. Now it is 1 by root 2, that means half of the ripple factor of the half-wave rectifier. That means full-wave rectifier ripple factor with pi section filter is double better. Here, final word of caution. When you actually design it, maybe in your laboratory or somebody asks you to design this filter, this X, that is impedance of capacitor, impedance of inductor that you are calculating, mind it, for half-wave rectifier, what is the impedance of a inductor? It is omega L or 2 pi f L, right? And for capacitor, it is 1 by 2 pi f C. Now, for half-wave, the frequency is F. For full-wave, frequency is 2F. That you have to always remember when you really calculate them. So here ends the chapter of filters, and next day or next lesson, we shall try to see in actual laboratory condition how these filters really remove the AC component of the rectifier outputs. Okay?